Welcome to the Mechatronics Revolution, Fundamentals and Core Concepts. In this lesson, we'll talk about the primary circuit elements we'll need to build electronic devices for mechatronic systems, and also the constitutive relationships that govern voltage and current. The learning objectives of this lesson are to review the concepts of voltage, current, and power, recall the constitutive laws for circuit elements, including resistors, capacitors, and inductors, and finally, we'll solve for the power of a DC signal and an AC signal. Electronics play a large role in mechatronic devices, and electronics design is a critical part. Electronic signals carry information between the microcontroller, sensors, actuators, and even between the user and the microcontroller. Electrical currents drive actuators such as motors, which are necessary for control and actuation of the overall mechatronic device itself. Let's review the main circuit elements. First, a resistor. A resistor has units that's measured in ohms. A capacitor has units measured in farads, an inductor with units measured in henries, and an ideal voltage source and ideal current source. These are the basic circuit elements from which pretty much any electrical circuit is designed. There's three main constitutive relationships that govern how voltage and current interact with these primary circuit elements. The first one is Ohm's law. Ohm's law says that the voltage drop across a resistor is equal to the current times the resistance. So V equals IR. Another constitutive relationship governs voltage, capacitance, and current. And that's given by the center relationship here that says the time derivative of voltage across the capacitor is 1 over the capacitance times the current. Finally, the constitutive relationship that governs inductance says that the time derivative of the current is 1 over the inductance times the voltage across an inductor. In addition to these primary circuit elements, a switch is also used often in electrical design for mechatronic systems. And it's important to understand what types of switches exist and how they can be used. On the left, we have toggle switches, and examples of these are shown in the center. There's various types of toggle switches. There's single pole, single throw switches, double pole, single throw, and double pole, double throw switches. And these indicate which current paths are switched on and off. For instance, in a single pole, single throw switch, by opening the switch, there's no current path. Versus in a single pole, double throw switch, by switching the switch itself, we change from one current path to another. And this is clear from the diagram. On the right, we have push button switches, and this is just a different mechanical design of a switch, where when we push a button, the switch either closes or it opens. The normally open switch has an open circuit when the button is not pushed, whereas a normally closed switch has a closed switch, and by pushing the button, the circuit opens. When switches are toggled, it's important to understand actually what happens. There's mechanical contacts underneath the switch, and when the switch is toggled, those mechanical contacts rebound. This rebound happens over a very short time scale, too small to see with the eye, but it's not too fast for a microcontroller. So we oftentimes see that when we switch an electrical circuit, the microcontroller actually sees us switch that multiple times. Here's an example of what the microcontroller sees in terms of voltage levels when we actually toggle a switch. The switch may start as open, and when we toggle it closed, it may close for a period of time, then open again, then close, then open again, and close. And that's called switch bouncing. And we'll see examples of that throughout this course when we use switches inside a circuit. Switch debouncing circuits or switch debouncing algorithms mitigate this effect. Another circuit element that's important to understand and use in mechatronic devices are potentiometers. Potentiometers, or rheostats, are variable resistors, and they can be tuned to precise values. We'll use potentiometers a lot for user interfaces so that the user can adjust the potentiometer and the microcontroller can sense the resulting resistance and understand what the user is providing. Another time we'll use potentiometers in circuit design is to adjust resistance levels to some precise value, since resistors only come in discrete values typically. And you can see the potentiometer symbol on the left of the slide. It's very important to understand the difference between alternating current and direct current, or AC versus DC. AC signals have a sinusoidally varying voltage, whereas DC signals have a constant voltage over time. And in fact, DC signals are a special case of AC signals. If we think about an alternating current signal as having a certain frequency, then a DC signal is just an AC signal with a frequency of 0. We can write an equation for an AC voltage signal as shown here using the sine function. Oftentimes we'll need to compute an average voltage of a signal or the average current of an AC signal. To do that, we typically use the root mean square voltage, so the RMS voltage. If we have an expression for the AC voltage signal, so we have an amplitude and we have a frequency and perhaps a phase shift of this AC signal, then these two expressions here show how to compute the RMS voltage. And then if you likewise have an expression for the current, then you can compute the RMS current for the signal as well using the expression shown. When dealing with AC signals, the concept of resistance has to be generalized to something called impedance. Impedance is a generalized form of resistance that applies to AC signals. When we have an AC voltage in a circuit, then impedance measures the opposition that the circuit presents to a current. So it describes the relationship between voltage and current when an AC signal is present. We will write impedance as Z, and Ohm's law for AC circuits is Z is equal to the voltage divided by the current. It's important to understand that Z itself is a complex variable because the voltage and the current are also complex for an AC signal. Z can be broken down into its real and imaginary parts. The real part, denoted as R, is what we typically call the resistance. The imaginary part, denoted by X, is the reactance, where J is the imaginary variable. So typically, for a DC circuit, we'll only have the real part, R, and we won't have the imaginary part because we have a DC signal. But in an AC signal, we have both resistance and reactance, and it's important to understand both of those quantities when computing the impedance. Let's talk about power. And power is a very important quantity to understand when we're building mechatronic devices so we can manage heat dissipation. Power is dissipated by a circuit element as current flows through that element. The equation for power is P is equal to I times V, but potentially for an AC signal, I and V are both time varying. So for an AC signal, we'll have an instantaneous power and we'll have an average power given by the expression shown here. For a DC signal, since I and V are both constant with time, we can write P is equal to IV, and then using Ohm's law, that becomes I squared R. Power is dissipated through circuit elements and becomes heat. When you design an electrical circuit, especially for mechatronic devices that may use substantial amounts of current, we have to make sure that all the elements in our circuit can handle that expected power dissipation. Otherwise, elements might overheat or burn out and fail. Power is measured in watts. Let's look at an example. For this circuit, we need to select a resistor that has an appropriate power rating. So we have an input voltage source at 12 volts DC. We have a resistor at 500 ohms, and we want to know how much power is going to be dissipated through this resistor. Using Ohm's law, we find that I is equal to V over R, which is 12 volts divided by 500 ohms, and that is 24 milliamps. Then we use the power relationship I squared R. So the current, 24 milliamps squared times 500 ohms resistance gives us 0.29 watts. So this resistor is going to dissipate 0.29 watts as current flows through it. So we have to select a resistor that has a power dissipation rating greater than 0.29 watts. If our power dissipation rating is below this value, then the resistor could overheat and fail. To summarize what we've learned in this lesson, there's key constitutive relationships between voltage, current, as well as the resistance, capacitance, and inductance of circuit elements, and these are routinely used in mechatronic design. Impedance is a form of generalized resistance, and it determines the current that flows through a circuit when an AC signal is applied. Finally, it's really important to calculate power dissipation through circuit elements to make sure that those components have the proper power rating and don't fail or overheat as current flows through them.